Example 101J. So before we start, for my subscribers, please share my videos to your friends, to your friends' friends, and to those who are new in my channel, please also do so because that's the remaining inspiration that I have in making this lecture and sample videos. It's very tiring on my part, but I tried my best to make the sample videos very detailed, and especially the drawing, the details, so that my viewers can understand well. And I will lose appetite in making videos if you do not share my videos to others. I'm creating a complete course. In fact, I name it One Stop Channel so that those who can explore my channel will no longer proceed to other bloggers or other channels. So that's my objective. This is more than uh, tutorial. This is more than a course. It is a complete course actually. It will be a complete course. So that I will not lose appetite in making videos. So that I will be inspired more. Please share my videos. I'm not selfish in sharing my lecture videos and my sample videos to you. So also do it to others. If I'm tired of creating videos, and you will know that, so please do so in sharing my videos. So here's the problem. This is solved in example 100J by double integration, and let's verify our answers by the area moment method. So determine the magnitude of P so that the first condition, the tangent at B is horizontal, and second, the deflection at C is 0. So let's compute, let's select B as our moment center, summation moment B 0. So AY times 5.4 plus P times 1.8 equals 1 half or 0.5 of 5.4 times 30, then 1/3 of 5.4 is 1.8. So AY is equal to 27 minus P over 3. So let's put it here. Then since we select B as the moment center, then moment due to this loading, the curve is third degree, first degree plus 2, so third degree, and the value of the moment over EI is equal to 1 half or 0.5 of 5.4 times 30 times moment arm 1.8. So this value here, so negative, and that's 145.8. Then the moment due to this reaction at B, first degree triangular area, 27 minus P over 3 times 5.4, that should also be 145.8 minus 1.8 P. So that the moment of this loading P at B is 1.8 P, negative 1.8 P. That's why the moment at B is negative 1.8 P. So since for the first condition, the tangent at B is horizontal, if the tangent at B is horizontal, then it will hit A. So that means the deviation of A relative to the tangent at B is 0. So that's the analysis. This is the tangent at B. It crosses point A, so the deviation of point A relative to the tangent at B is 0. So that's the analysis. And it is equal to the moment of area of the M over EI diagram with respect to A. So this is equated to 0, and 0 equals 0.5 of 5.4 times quantity 14 times 5.4 times quantity 145.8 minus 1.8 P. Then 2/3 of 5.4, this distance is 3.6. 2/3 of 5.4, 3.6. Minus the area of this third degree curve, which is 1/4 or 0.25 of 5.4 times 1/4, 5.8. Since this is 5.4 over 5, so this distance is 5.4 minus 5.4 over 5, or simply 4/5 of 5.4. The distance of the centroid of the third degree curve from A is 5.4 minus this distance is 5.4 over 5, where 5 is n third degree plus 2. Simplifying, combining the constants, 0.5 of 5.4 times 145.8 times 3.6 minus 0.25, 5.4, 145.8 times quantity 5.4 minus 5.4 over 5, that would be 566.874. Then for the p's, 0.5 of 5.4 times 1.8 p times 3.6, so that's negative 17.496 p. We can now solve for p. 566.8704 divided by 17.496. So p is equal to 32.4 kilonewtons, just like in double integration method. Then for part B, the deflection at C is 0. So this is a different case. So the slope of the tangent at B is no longer horizontal. So this is the expected elastic curve, and we compute EI deviation of A relative to the tangent at B, which is now this one. So we copy the same terms, except that we do not equate it to zero anymore, because the condition in part B is different from part A. So there is now slope at B. So we just copy this, then times 3.6 minus 0.25, 5.4, 5.8 times quantity 5.4 minus 5.4 over 5. So we get the same expressions, but this is EI division of A relative to B. So EI division of A relative to B is equal to quantity 566.8704 minus 17.496 P. Therefore, theta B, so this is the tangent at B, this is the deviation of A relative to the tangent at B, and this is theta B. This is also theta B, the angle that the tangent at B makes with horizontal, which is positive because it is inclined up. So theta B, the analysis is we have here deviation of C relative to B, which is expected negative because the area is negative here between B and C. So this vertical distance, so that the deflection at C would be 0, should be the vertical leg of this right triangle. The vertical leg of this right triangle is expected to be 1.8 of theta B, and it is above the horizontal axis. Deviation of C relative to B is expected negative. Therefore, deviation of C relative to B, which is negative, plus 1.8 of theta B, which is expected positive, must be 0, so that the deflection at C would be 0 as shown in this figure here. So let's compute EI division of C relative to B also. So theta B is division of A relative to B over 5.4, and it is positive. So theta B is 104.976 minus 3.24 P over EI. Then EI division of C relative to B is area of this curve, then distance of centroid from the right, from C, is 2/3 of 1.8, so 1.2. So the area is 1/2 or 0.5 of 1.8. So negative 0.5 of 1.8 times 1 point P. Then moment arm 2/3 of 1.8, so 1.2. Simplifying, deviation of C relative to B is negative 1.944 P over EI. We then substitute into this equation. So negative 1.944 P over EI plus 1.8 of theta B, quantity 104.976 minus 3.24 P over EI equals 0. So cancel out 0. Cancel out EI rather, or cross multiply. So combined the constant 1.8 times 04.976, then negative 1.944, negative 1.8 times 3.24 to the right. So 1.8 of 104.976 equals positive 7.776p. Finally, we can solve for p. 1.8 times 104.976 over 7.776. And p is equal to 24.3 kilonewtons, just like in double integration method. So that's it. If you like my videos, don't forget to share. And for those who are new, please subscribe, because no bloggers have developed a channel which uploads many example and lecture videos. So this is more than a course. That's why I call this one-stop channel.